Everybody, welcome to yet another Codeforces training. Today we'll talk about lowest common ancestor, which is pretty important topic once we get ratings like 19 to 2100. So somewhat advanced, but the algorithms that we will cover today are not particularly difficult. So if you're a regular Div2 contest participant, then it's very well possible that at some point you will find this useful. So let's get started. First, I'll explain the setting of the problem, right? So in lowest common ancestor, we have a tree. A tree is rooted. That we have like root. It has several children. These children in turn have their children, or potentially they don't have, like this one does not have anything. And so we have a rooted tree. We receive several queries of the following type. We're given two vertices, and we want to find their lowest common ancestor. Well, the ancestors of this vertex are the following. We first go to parent again, right? And we go to parent until we get to root. In the same fashion, we can find the ancestor of the second vertex, right? So we have you and we. We can just go to their ancestors, their parents. So ancestors of u is the following set. Well, first of all, u is considered to be an ancestor of itself for the purposes of specific edge cases. Then we have a parent of u, parent of u, etc. And in the very end, we always have root, because every node in the tree is an ancestor of root, a successor of root. So root is the ancestor of every node in the tree. And the same holds for every vertex. And you immediately can recognize that these vertices have at least one common ancestor. So no matter where both of them are in the tree, the root is always a common ancestor for them. But maybe there are some more vertices that are located lower in the tree that are also common ancestors. For example, here, this vertex is an ancestor of both u and v, and it's lower than root. So we should return this vertex. And yeah, of course, vertices are numbered. So usually root is like 0, and you have like, I don't know, 1, 2, 3, 4. Specific order does not matter. Usually graphs of this type are given in the format like parent of first vertex, parent of second vertex, etc. But it's not necessary for our algorithms to work. I think I'll leave numbers for now, just in case we need them later on. So actually what we already explained is an algorithm, right? We create this, I don't know, vectors, whatever container you like, stacks potentially. And then as long as their last elements coincide, you just pop them. And whenever you first hit two different elements, and you know the last element that you popped is indeed the answer. And in some cases, for some small constraints, this is sufficient. Let me clear all the drawings temporarily, and let's consider first problem. In first problem, LCA begins. We have 8 most 1000 queries. Well, you may say that, like, wait a second, this problem is different because here we have add queries and get queries. And the truth is that it's not. It's not. Like, because we never delete vertices from the tree, we may assume that it's all add queries are processed before all get queries. There are some specific cases for online LCA, but in most problems you'll face so-called offline version, so that you can process queries in whatever order you like. You just have to return answers in the correct order. And for small trees of size 1000, for 1000 queries, to get lowest common ancestor, as described, algorithm works just fine. You can get ancestors of the given vertex, get ancestors of both vertices for which you want to compute the lowest common ancestor, and just iterate. Like, until you're good, you update your answer. As soon as you are not good, you can break. So here, for example, we could say if current ancestors are different, then we can break immediately. But it's not necessary. Yes, so each query is answered in the time big O of the size of the tree, which is of course very slow, or should I say in big O of height of the tree. So in fact, if your trees are balanced, this straightforward algorithm works just fine. It works in logarithmic time if your trees are balanced. But in practice, somewhere on Codeforces, I believe everywhere, like there is a test case with the generate tree called a bamboo. Now, bamboo is, of course, a tree which is a path, straight path, right? In such tree, like height or depth, whatever you call it, is equal to the size of the tree. So this algorithm will work in quadratic time, which is of course unacceptable, right? If you have more than 1000 vertices and queries. So let's talk about bigger versions of the problem. In fact, there is a typo. So in problem B, LCA continuous, both values should be 500,000. I should update it. And we'll see that if the size of the tree can be 500,000, then of course you need to do something smarter than quadratic algorithm, right? You still can process queries offline, right? But the algorithm that you want to use will be different. Not particularly difficult, but different. Yeah, let me just update the statement so they don't look strange. All right. So here we can have 500,000 queries. And of course, we need something more, something smarter, okay? Now, there is a method for such problems. I hope Yes, okay. So I never clicked anything bad, so the buffer still contains this tree. Okay. Let us change our approach to something a bit smarter. I hope I can, yes, okay. So first of all, we will need to run a depth first search on our tree. And the purpose of running depth first search is the following. For our algorithm, we would like for every pair, given a pair of vertices, we would like to quickly determine whether or not one is an ancestor of another. And if you have some experience with DFS, then you can say that vertex U is an ancestor of vertex V if and only if and only if time in which DFS first visits vertex U is before time when DFS first visits vertex V and time when DFS leaves the vertex U, right, is greater than equal to time when DFS leaves vertex V. And the DFS with time is very simple. Whenever you do anything in your DFS, you just increment the time counter. Let's see on the example. So initially we have like a timer equal to 0, right? And we start our DFS at R. We'll also write down the order in which we visit vertices for convenience. So first we visit O. I will denote time in, no, let me use. So we have time in and time out. Was these are arrays. So first we visit vertex 0 and time in at 0 gets 0, right? Pretty reasonable. And timer gets incremented by 1. Let me also decrease our tree a little bit because otherwise DFS will take us forever to figure out. Okay, so then we go to this vertex or maybe to this vertex, but I'll assume that left to right is the order in which vertices are given in the adjacency list. So in the list of children of vertex R. Okay, so then next vertex that we visit will be vertex 1. So time at which we enter the vertex 1 is 1, right? And timer gets incremented by 1. Now, there is nowhere to go from vertex 1, so we immediately exit vertex 1 at time 2. So here it will be time at which we exit a vertex root. Right? And we again add the current vertex. So whenever we enter or exit the vertex, we add it to our order. So here we have order. Right? We exited the vertex, we increment the counter, the timer, and we go to the next child of root. At the vertex 2, we first visit it at time 3. we add 2 to our order. I will decrease it even further because no, actually, let's leave it as it is. So we entered vertex 2. We put the correct value into our time in. We update the counter. We go to vertex 3. We enter and exit vertex 3. Then we enter and exit vertex 4. And they get what times? Time in at 3 gets 4, time out gets 5, time in at 4 gets 6, time out here gets 7. Now our timer is 8. So we went like this, then like this. Here it's 8. We exit vertex 2. And we again add it to our order. Actually, you know what? I was wrong. I was very wrong. We add vertex to an order whenever we return from its child. So here order should be like this. I believe the correct order is like this. So we add a vertex to order whenever we, so first when we enter it and then when we return from its child, right? Okay, so we are currently here, we'll go to 5. We visit 5, we visit 6, we return from 6, we return from 5, we are done, right? Let me just quickly fill in the times. So we enter 5 at time 9, we enter 6 at time 10, we exit 6 time 11, we exit 5 at time 12, we exit 0 at time 13. Again, our path was as follows. We went there, and here, here, and here. So now we have time in and time out, and we can quickly check whether or not vertex is an ancestor of another vertex. Let me demonstrate it. For example, we have vertices 3 and 2. Now, yeah, I'll put indices because otherwise I'll just mess it up. I have 2 is we are in the subtree of vertex 2 from time 3 to time 8, and we are in the subtree of vertex 3 from time 4 to time 5, which means that subtree of vertex 3 is inside the subtree of vertex 2, and 2 is an ancestor of vertex 3. If we were to take like 3 and 5, and these intervals are non-overlapping from 4 to 5 and from 9 to 12. So none of them is an ancestor of another one. Also, it works not only for direct parents, so for 0 and 4. 4 is active from 6 to 7, and 0 is active from 0 to 13. So 6 from 7 is inside of 0 to 13, and hence 0 is an ancestor of 4. So once we run this DFS, we now have a very specific order of vertices, and we have time at which we first visit the vertex and time at which we exit the vertex. It allows us to quickly check whether or not a vertex is an ancestor of another. Now, this alone does not solve our problem. because with this tool, we can check whether one of the vertices for which we want to compute LCA is an ancestor of another. If U is an ancestor of V, then obviously LCA of U and V is simply U, right? Because U is ancestor of itself, it's ancestor of V, and it's obviously the lowest ancestor of U. It's the lowest common ancestor. However, vertices 3 and 4 have a common ancestor that is not, that is neither of them, right? So 3 is not an ancestor of 4, 4 is not an ancestor of 3, but they have a lowest common ancestor of 2. But this is helpful already. And the reason why it's helpful is because of the very interesting idea of a binary lifting. Let me clear this mess. So I believe by now you remember this criterion of whether or not U is an ancestor of V. I'll just leave it like so that we know that we have such operation, which after we run DFS runs in linear time in the size of the tree. So after we run DFS once, we can answer each query of such type in constant time. Just have to access 4 values. Now, what we can do with binary lifting, I think we'll need just for pedagogical reasons, we'll add our vertices back that we deleted. We won't need order just now. So we don't need order in the version of binary lifting that I want to discuss, but we'll need it a bit later. So I'll just leave it back for now. The reason why we did not want to go along the path to the parent for huge trees is because they can be very deep, right? Let me add even more vertices. Let it be the vertex number 8. And somewhere around, let me think, somewhere around here, I'll add vertex 9. Suppose we want to find the LCA of 9 and 8. Well, first of all, we check whether one of them is the answer, right? If neither of them is the answer, so neither of them is an ancestor of the other one, then we know that we have to go upwards, right? How do we go upwards exactly? We know we can always go to root, right? But it's a little bit too much. We'll skip the correct answer. So what is the max step that we can take? Well, without knowing what is the LCA, we can't say for sure, right? All we can do is quickly check whether or not the vertex to which we went is an ancestor, right, of this vertex. Now, if you, for a second, disregard anything in this tree except for the path from first vertex to the root, and think about in terms of quickly computing some function, and you want to find the smallest value for which the value of argument for which the value of function is true, and you will immediately recognize that it's a binary search, right? So the strategy to find this vertex is the following. We ask about the middle, and we can ask about the middle in the following ways. So suppose we know the depths. Obviously, DFS can compute depths of vertices. Then we would like to go to parent on some bigger depths than 0, right? Unfortunately, if we store parents for all depths, for all what is my first parent, what is my second parent, what is my third parent, and obviously it results in quadratic memory usage. So we can't store each parent. But what we can do instead is something called exponential search. So we can store first parent, we can store second parent, we can store fourth parent, and so on. Now, if you are familiar with exponential search, then you know that it also runs in logarithmic time. If you can always add any power of 2, or actually, does it always run in? Well, in this particular case, it always will run in logarithmic time. I believe in some cases that are not exactly called exponential search and can run in square of log time. But anyways, so suppose we store first parent, second parent, fourth parent, eighth parent, etc. Right? For this tree, we only store up to 4 parents. Then we can take first parent of first vertex and ask whether or not first parent is an ancestor of this vertex. Right? If it is, then Lca is here. Right? Okay, so we want to go to the parent, but not that much. Okay, let's go to the second parent. Now we are here. We again ask whether this is a parent, is ancestor of this. And the answer is no. We now know the answer is somewhere here. We can use a smaller step of first parent and then ask whether it's an LCA or not. Eventually decreasing the number of the size of the step, we will get to the correct answer. And it's not necessary for depths to be exactly power of 2. As long as we have enough powers of 2, we'll be able to represent any parent in this interval by some combination of logarithmic number of these elements. It's obviously base 2 numeric system, right? Binary system. We can go to fourth, we can go to second, we can go to first. It means that we can go to any parent between first and seventh, right? Okay, so this is the algorithm. In logarithmic time, walking to parents, but not direct parents, but to fourth parent, second, potentially in some cases to, I don't know, 1024th parent. That may happen if you have 500,000 vertices. Yeah, but again, depth of the tree is limited by a log of its size. No, actually, number of powers that we need of 2 is limited by log of the size of the tree, right? And so we only store log, it's supposed to be log of, let's say the size of the tree is n, and for each vertex we store that many parents, and we have n vertices, so our memory usage is n log n. And we answer queries in logarithmic time. Pretty decent algorithm. these parents can be computed very conveniently. We'll take a look at the code in a second. Actually, yeah, let's already do this. So we, for aesthetic purposes, I created a class that handles everything. It runs depth first search inside when you call initialize method, and it also has like is ancestor method private, so that you don't have to worry about how it works. It can append vertices if you have some sort of dynamic problem as well. It's not necessary to give it the entire graph at once. So, like, what is the max power? Well, max power is a log of size. If you don't want to compute log slowly, then you can use something like 31 minus count of leading zeros in size. But this is initialization, like nothing interesting happens here. What interesting happens is whenever we append a vertex, first parent, so 0 represents the power of 2. So 2 to the power of 0 is first, right? First parent is just whatever parent you ask to append to. Then interesting things happen. What is the second parent? Second parent is first parent of vertex. Who is the first parent? First parent is second parent of vertex. Who is eighth parent? Eighth parent is fourth parent of vertex. So you just access parent once, get a vertex, access parent again with the same depth of power -1. Just like that, like in literally 3 lines of code, if you disregard this bracket on its own line, then in literally 3 lines of code, you can compute parents for all interesting depths. And then compute Lca is very simple. You check whether first is ancestor or second. If so, you return first. You check whether second is ancestor or first. If so, you return second. Otherwise, you iterate through powers in the descending order. This is what you do. You go to some parent if it's ancestor. Then if it's not an ancestor, then you go there. If it is an ancestor, it means you need to go up, but not that much up. Once you converged, you return the answer. So whatever vertex is now first, it's the correct answer. So entire implementation of Lca class, almost entirely, is mostly visible on the screen. If you don't separate implementation from declaration, right? Actually, is it a declaration or a definition? I'm not sure. Whatever. I mean, if you don't separate the implementation, then, and also use like shorter variable names, an entire Lca with binary lifting takes, I don't know, 40 lines at most. For example, here I have a line break just because I wanted to use long variable names. Here I have like 1, 2, 3, 4. Okay, 1, 2, 3, 4 unnecessary lines. Right? If you don't like curly braces, you can get rid of them very easily. So binary lifting is very easy once you get the idea. And this is sufficient to answer 5,000 queries in 1 second. Actually, in 2 seconds, but I believe my solution works in 1 second as well. Also, in fact, like this problem is back from 2012, 2013, but these constraints were pretty mad for that time. So if you submit to this chaining on Codeforces, then your running time will be multiplied by 2 because Codeforces servers updated since then. So actually, if my solution display time is 1 second, then it means the real runtime is 0.5, so half a second, right? And I believe, actually, I can check. I think that this problem is solved in some lower time than 1 second. By the way, because I participated in some D1 contest and got plus 100 rating, I now have access to add problem statements translated directly to the gym, right? So you will find problem statements. You don't have to go to my GitHub by link. You will have the same link in the training itself. Where is it? Here it is. Oh, actually, okay. Right. My solution runs in exactly 1 second. So the real time is like 0.5 seconds. And I believe that nobody will give time limit of 1 second for LCA currently. So it's like 4 times safe from getting time limits. And also 500,000 vertices is unlikely to happen. More like 200,000, maybe 100,000. I don't know. It's also a reasonable constraint. So yeah, it's pretty safe to implement it like this. I believe you can have a couple of optimizations. However, I'm not sure like straight away what would be these optimizations. Yeah, I'm not sure. Whatever. We have two more problems. Problem C, which is called LCA minimum query, and minimum query stands here for a good reason, is absolutely mad. It has only 100,000 vertices, but it has 10 million queries. And for the purposes of not having huge input files, these queries are encoded in some smart way. But it does not make problem online, so it's still offline. You can add all vertices, all. You have like your tree straight away, and then you have to answer queries. So it's like semi-online because you have to answer queries in order, but tree is given straight away. And for these purposes, logarithmic complexity for finding LCA is not sufficient. If you submit like this, you will get TLE. I believe my current solution, which finds LCA in constant time, after some pre-processing, works in like 1 second. So it's only 4 times safe from time limit. And for these problems, actually, 4 times is okay. So in SPBSU, they have like as low time limits as possible to make sure that every reasonable solution passes, but no unreasonable solution passes. So here we need something new. And I hope. Right. So let me clear this mess. Now order comes into play. And I will remind you how we constructed the order because somebody may have already forgotten about it. Let me bring back some parts or graphs that are missing. If here was 1 and here was 5, also somewhere was 7, but I'm not sure where. I'll pretend that it was here. I don't remember, honestly, and it does not really matter. So here we had like 1, 5, 7. And because I modified the tree, I'll need to compute the order again. So we enter vertex 0, we go to 1, we return from 1 to 0, we go to 2, we go to 3, 6, 8, we return from 8 to 6, return from 6 to 3, from 3 to 2, from 2 we go to 4, from 4 we go to 9, from 9 we return to 4, return to 2, return to 0, go to 5, go to 7, return to 5, return to 0. If you count, you can figure out that the length of this order is 2 times n minus 1. Because for every edge, whenever we traverse edge like in new order, we add its endpoint. Right? Like we first traverse this edge in this order, we add this endpoint. When we traverse in this order, we add this endpoint. So in fact, we actually always add the vertex to which we go along the current edge, right? And except we not only need these numbers, we need some more numbers, which will be the following numbers. For this vertex, the number is 0. For this, it's 1. For this, it's 2, 3, and 4. I believe you can already spot where this is going. We need depths of vertices. Here we have layered structure. Depth is 4, depth is 3, depth is 2, depth is 1, 0. Obviously, DFS can compute depths. You just need to pass it, and you don't need to. You just create vector, and whenever you go to vertex, if you know the parent, then you can add +1 to depths of the parent, right? Now, let me write the depths of these vertices in the given order, okay? For that, I believe we'll need to bring it a little bit up, and this will need to bring a little bit down. What are the depths? For 0, it's 0. For 1, it's 1, 0, 1, 2, 3, 4, 3, 2, 1, 2, 3, 2, 1, 0, 1, 2, 1, 0. Interesting fact about this depth sequence is that all pairs of adjacent elements differ only by 1. So it's either +1 or -1 in depth. And it's reasonable because every edge in the tree goes either down 1 or up 1. Okay. Okay. Now, even more interesting thing happen. Suppose we still want to find the LCA of 8 and 9. We then take a look, what is the first position when these elements appear here in the order? And if you look between them, you will find interesting things. So everything that was here in subtree between these vertices lies between them in order. In particular, LCA lies between first occurrence of these vertices. And of course, first occurrence can be just stored somewhere in the vector, indexed by vertex ID. But how do we find LCA? Now the depth comes into play. LCA Lca is now the highest vertex between these two. So it has minimum depth. And we effectively reduce Lca to range minimum queries. So we want to find a minimum on every range. Specifically not the value of minimum, but the index of minimum, but it's more or less the same thing. So here, for example, we would like to return, let me think, 9, I believe. Here is like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. Yeah, these digits are pretty awkward. Whatever. So we want, now we want to find range minimum queries in constant time. And you may or may not be familiar with range minimum queries, but the method to find RMQ in constant time, if you are allowed some pre-processing, is sparse table. Sparse table again lies on the ideas of having answers for intervals of some universal length. So for each cell of our array, we effectively have an array of depths. We will store what is the minimum on the following segments. So we have segments of length 1, 2, 4, 8, etc. until we run out of the boundaries of the array, then we don't want to store this. For example, here is the bright boundary of the array, then we don't compute like 16 because it makes no sense. There is no such interval. You may already see where it is going. It will obviously take linear arithmetic memory, right? So n log n. Because I have again n elements, and for each we store log n values. And the way to answer RMQ in sparse tables is find whatever is the max power of 2 that fits between. So here it will be 4, and ask 2 queries. 4 to the left, 4 to the right. Because it's the max power of 2, they will cover the entire subsegment, right? You can't fit 8 between them. It may mean that the first 4 and last 4 are all the elements. Because if these do not intersect, like here is 4, here's another 4, then you can fit 8, right? So now you're just interested in find first occurrence of this and this, find max power of 2 that fits between them, make 2 queries to sparse table, so a constant number of queries. Sparse table is of course random access. So 2 queries to sparse table cost constant time. And you just take whatever is best of 2. Here, it would be this, because it's in boss. It could happen that it best is in fact in only 1. If we had like some other query, then again, nothing bad happens, like which is this query answers this element, this query answers this, and we select whatever is best. So as simple as it gets. You reduce Lca to RMQ and then solve RMQ in constant time per query with some memory overhead. Now, there is, I must tell you, there is Farah, Colton, and Bender's algorithm that solves Lca offline in linear time. And offline means purely offline, I believe. No, actually, that's a different algorithm. We can solve, yes, yeah. We can solve Lca online in linear time. So constant time per query. And the key is that like you can have a smaller number of blocks and still answer queries quickly. The specific value at which you want to cut the blocks, I believe, is log n. Or something like this. I'm not entirely sure. And the economy will come from the fact that there are not many different blocks of this kind because a specific plus minus one property of depth array. But we won't get into these details. I know several problems where this is necessary, but it's like EJM level plus. So I have not seen a problem on a real contest that requires linear LCA. Sparse table is already good enough. If you have, I mean, it solves 10 million queries in 1 second. So I don't remember like recently that it was necessary to solve it even faster. And usually you're fine with linear arithmetic construction time and memory. If you are not fine, then I guess you can have some memory optimizations. Like if you start offset from the beginning, then several first elements can be made like int 16t, anything like that. I believe once we were solving some kind of problem where like crazy memory optimizations were necessary, but it's usually not the case. So just this version works fine for this problem, and it will work fine for most reasonable problems that you will encounter like in nearest future. And I believe nearest means around next 10 years, definitely. So yeah, this is it for sparse table-based LCA. We can take a look at my code if you want to. I think you want to. So again, structure with powers remains, but now we have not parent but sparse table. This code looks suspiciously familiar, but now it's sparse table instead of parents. And sparse table is computed just in the way that, right, I did not explain how to compute sparse table. Well, it's pretty clear, like if you want to compute what is minimum on the segment of length 2, then you have to compute minimum on first half and on the second half. If you want to compute for length 8, then you want to compute first 4, last 4, take whatever is best. It's exactly what happens here, with the only exception that we do not always have right half if it's like outside of the array. To compute LCA, again, constant number of cores, we find whatever is best, whatever is max power of 2 that fits between. And built-in count leading zeros is, again, it's just the fast way to compute logarithm. And we'll talk about all these bitwise operations in the next educational video. It won't be about Codeforces because Codeforces does not have such trainings, I believe. It will be on a different platform, so stay tuned if you want to find out how to use all these binary operations built in CLZ, pop count, etc. And good news from STD, from C++20 onwards, all of this stuff is in STD, right? So in header bit, I believe. We can take a quick look at what I mean. So from C++20, we have bitwise ceiling, bitwise bit floor. It's smallest power of 2 that is not less than given value and so on. So bit floor, I believe, is what I'm currently using for logarithm. Also count leading zeros and stuff like that preserves pop count. Yeah, so all of this stuff will be in standard from C++20 onwards. So good times are coming our way. I believe C++20 was released like when? Months ago, December 15th, something like that. So yeah, here LCA computation is even simpler. All the work is done in initialization, just like that. Also remember that you want to push to order whenever you return from a child. So for every successor, you want to, actually it's not a successor, it's a child. A successor means undirect child as well. Okay, now it's semantically correct. Just like this. I don't know if you have any questions, definitely ask me in the comments. Like this part is only implements generation of queries. There's nothing smart here. Again, it's like very short. If you disregard main functions, it takes like, I don't know, 30 lines around so. Also includes -10 lines. I believe around 20 lines you can save on something like this. Not on all of them, but it's clearly this if does not need its brackets. This for does not need. Empty lines are completely unnecessary. So around like 70, no, 70 is too much, like 60. If previous version was around 40 lines, I believe this is like 60. And also if you don't use like, if you don't mark everything that's constant by const, then you obviously can fit these two on it, the same line, this two on the same line. So yeah, very short code. Much simpler than Farah, Colton, and Bender algorithm, which is the one in linear time. But it is also not like very complex. It's just like 100 lines of code. We don't want to get into it today. Maybe later. Now, sometimes LCA comes into play in very strange, on the first look, setting. Problem D is color wizards. I'll quickly explain the legend. So we have a graph, which is not necessarily a tree, but the graph is rooted. So we have a root, which is called capital. And we have many queries which ask about the following, like we want to go from 2 vertices to the root in such a way that the length of the common path is as small as possible. Now, obviously, it translates to finding depths of LCA of these vertices, right? But what is LCA if you have a graph and not a tree? It's not obvious. Now, luckily for us, once you compute strongly connected components and bridges, now I believe here we definitely need to show something. We have root. Root is in its own connected component. Possibly there are other vertices as well. Then we, like, if you look at the structure of connected components instead of vertices themselves, then the structure of connected components is a tree. It's a tree, right? So, but here interesting things can happen. So if you and we are like so, then you can just compute LCA, and you compute depths in terms of edges between different strongly connected components. But what if something like this happens? Well, not a big deal. Once you get to this component is strongly connected. Strongly connected means that we can have two different ways to get to this vertex without common edges. Because if you don't, then it's not a strongly connected component. So we are still interested in finding like LCA in terms of strongly connected components and then finding its depth. Now there is a linear time bridge finding algorithm. I believe it's called like Tarjan's algorithm or something like that. And I'm very lazy. I implement, okay. I believe I implement merging vertices in components by disjoint set union. It's another nice approach, very like little code necessary. So whenever you see the two vertices are in the same connected component, you can merge their components by disjoint set union, which is like union find. In this, I believe it was from some programming class. So I have like a very reasonable class structure. I have bridge finder, DSU, components builder, which builds components given a graph. I believe it. Yes, it takes like bridges and then finds merges everything that's not a bridge. And we have LCA computer, which actually works in problem B. So it's a binary lifting based approach. Right. Here's binary lifting again. Components builder just uses union find. So yeah. Don't be scared of that class structure. It just for the purposes of having a very short code in main. So here we have like once we initialize the graph, we just run bridge finder. It gets us bridges, and we build components from bridges. We get components. Then we have a tree of components, right? And then we run components. We run LCA on tree of components. So yeah, like all this class structure was necessary to have like this very, very short main code. And it's also useful because you can debug classes each on its own. It's nice programming practices help in competitive programming as well. Well, obviously in CP, I would have like class LCA and not LCA computer. Instead of is Ancestor, I would probably write up. Time in is teen, time out is tot. Adjacent is 2, vertex is V, parent is P, graph is G, timer is T, etc. But you get the idea. Also, this is not correct. It should be uppercase, but whatever. So yeah, like sometimes problems may not be solvable by LCA alone. Sometimes it's like you're given a graph and you want to figure out what kind of LCA you need. But this is pretty involved problem. Okay, if we go to training standings, like when training was live, right? So a lot of people solved A, obviously, a lot of people solved B. Not that many people solved C because it's not obvious, right? You need more involved approach with sparse table, and very little people solved D. Now, if we go to standings, we will find post-contest statistics as well. And let me clear this, we no longer need this string. So almost everyone who's tried solving A solved A. Like around 80% people who tried solving 85, who tried solving B solved B. Around 70% people who tried solving C solved C, and the same for D, but the number of correct submissions even in practice decreases. You can see a lot of people who solved like ABC and did not solve D. And also you can see people who solved ABD and did not solve C. Some of them are even grandmasters. International grandmasters, I believe. Right. As you can see, like these kinds of trainings are pretty popular in my country. So we have like people from all over the country solving these trainings. Like 5 years later than it was released, right? Here we have like 3 years later, then 3 years later, 5 years later, right? 4 years later. So these trainings are still all these years after they were released, they're still interesting and very educational. Especially like this is pretty involved. Okay, Lost LCA is not a beginner's topic. So once you get like to 20, 2100, I think you want to learn LCA. In particular, because like you can learn it earlier. It's not difficult. Like once you get the idea, code is very simple, both for binary lifting and sparse table. But yeah, but you just want to see these problems often at lower ratings. And potentially from like D1, you can see them with some periodicity. But still, LCA is like not the most popular topic, but it's an important one. So if you have time to learn it, I encourage you to do so, to write your own template. You will obviously can copy my template, but I did not stress test it enough to guarantee that it always works. So it will be your own risk. Like I'm pretty sure that it's correct, but you need to test all edge cases accurately. So thanks for watching. If you have any question regarding LCA, ask me down in the comments below. Later this week, you will be able to ask me questions not in the YouTube comments, but on Discord. But it's still work in progress, and it will be for a couple of next weeks. We'll still make some adjustments, but stay tuned. We'll have Discord soon. So you'll be able to ask me a question like whenever you need to and not necessarily about a specific video, right? And also, with all this binary lifting and binary operations involved, we'll have a video later this week I'm not sure. I think it will be on Friday, but maybe I'll record it a bit earlier. And yeah, about bit manipulations. It won't be on Codeforces, it will be on binarysearch.com. It has like around 16 problems on bit manipulations. I'm not sure how, like I already solved all of them, but I'm not sure that we need to go through each and every one of them, but we'll go through like around 10. So you'll get pretty good understanding of what are all these bit manipulations about. So yeah, stay tuned for more content. Hope you enjoyed. Hope you find all of this useful. Great. And with that in mind, see you next time.